We're outside the studio recording The Flying Mice, our next segment here on The Tonight Show. Here's a sneak peek.
Hi, I'm Greg Goolsby.
And I'm Garrett Ann's. This is The Tonight Show. Tonight we're going to be talking about Mousetrap cars.
Specifically, our design.
So this beautiful car is the Flying Mice, named after the Flying Tigers of World War II. We got the design right here. Alright, the reason why we designed our car like this is because, well, to start, we used a standard Victor mousetrap as the frame. This makes it more lightweight. CDs were our wheels because they are thin and light. Makes sense because we wanted a lightweight design. So,
That
for
we
the
did,
axle,
Garrett. That we did.
we did. For the axles, which is that part right there, we used stripped down pins. These pins won't be used right anymore. That was a good one.
Yes, sir.
Woo! And then we put 2 eye hole screws on each side for rotation, so the car could move, of course. A string was tied to the original lever and the rear axle. We used a hot glue gun and balloons to hold the CDs to the axle, thus creating the Flying Mice.
Now, one major problem we ran into during the design of our car was how to create friction between the wheels and the ground. And to solve that, as you can see these black things around our CDs, we added latex balloons around the wheels so that they could have more traction. And then at the axles, friction is created between the pin and the eye hole screws and is released as heat, which eventually brings the car to a stop.
Traction. The balloons around the CD wheels create a larger coefficient of friction. This leads to more grip on the ground, road, or, in our case, the science hall. The weight of the car pushes against the ground, increasing traction as well.
Greater power. Okay. Next, we're going to talk about the effect of altering the lever arm on power output. As you can see, we went with the smaller lever arm, the original lever arm, to keep our design nice, compact, clean looking. However, the longer lever arm allows for a greater power output because it allows the lever to travel a longer distance over the same period of time, increasing power.
Good? Isaac Newton. What a man.
Right you are, Garrett.
He's
a
quite the
man.
man. Alright. Obviously, our car follows Newton's laws of motion. So, we'll start with the first law, shall we? The design of the Flying Mice was had a light mass causing a higher acceleration. F equals ma. We got a smaller m, a bigger a. Same amount of force because it's a mousetrap. And everyone was using Victor mousetraps. The second law of inertia. Our mousetrap would continue to travel in a straight line if it weren't for the friction of the ground and the friction caused by the axle rubbing against the eye hooks. Those pesky eye hooks. And the third law, in equal and opposite reaction. The lever and the string pull against each other, creating tension in the string. This makes the axle rotate, causing the car to move, of course.
There you go.
That's right.
Of course, our mousetrap car is completely dependent on energy for motion. So at the very beginning, when we set our mousetrap, energy is stored in the spring, and when it's released, the elastic energy stored in the spring is converted into kinetic energy as the lever moves forward, pulling on the string and rotating the axles. The friction between the ground and the wheels and the axle and the eye hooks reduces the energy in the system as it is released as heat. The trap, specifically the spring, does work on our car as it pushes the lever forward, in turn pulling the string and spinning the axle, creating motion. For all of us here at The Late Show, we want to thank you for watching. Good night, and God bless America.
Have a good night.